Okay, section 8.2, we're looking at transverse and longitudinal waves. Okay, so a transverse pulses. Okay, so what a pulse is just a short disturbance, usually just a crest or a trough. And so if we think like a pulse could be like throwing a rock into water or something, it causes a trough and then the waves kind of go out from it. Okay, so looking here, if our hand is holding a spring, okay, the hand starts at equilibrium position for the spring. Okay, if you create velocity of your hand going up, it sends a pulse from the front of the pulse starts to move along the spring. Okay, the hand continues to move up, okay, until the hand is at maximum amplitude. As it comes down, okay, till it's at the hand moves towards the equilibrium position. Okay, the amplitude of the pulse moves along the spring. Okay, and so again, the amplitude's from equilibrium position up to the crest. Okay, and then the pulse is complete when the hand is back at equilibrium position. So this creates this crest, which then would run down the wave as it went. Okay, so a transverse waves, or for transverse waves, the displacement of the medium is perpendicular to the direction of the wave of travel. And so if, like in this case, this is a transverse wave, it's on the floor. So the direction of travel down the spring is this way. If you go side to side, like if you shake this spring side to side, the displacement, okay, is actually side to side that's going out. Okay, and like for this one, okay, again, like for even this example we started with, whoops. Okay, the velocity of your hand moving up, okay, or down, or I guess your hand would start up and this would cause this spring to go like this. The actual displacement is going this way, and so but the velocity is going the other. Okay, energy changes during the movement of a pulse. Okay, so again, looking at a spring, okay, at our crest here indicates, okay, we have our maximum potential energy for our spring, okay, and then our EK is 0, and then it would move down. Okay, this is where our EK, like we have energy, both potential energy to go back to equilibrium, and there'd be some velocity energy pulling the spring back this way. So the amplitude of a wave can be used to determine the quantity of energy that is stored in the pulse. Okay, longitudinal waves. Okay, this is we have our spring in equilibrium position. Okay, a longitudinal wave is where you coil some of that spring up and then you kind of let it go. And so like that coiled up part would run along the spring all the way. Okay, so a longitudinal wave, okay, the displacement of the medium is parallel to the direction of the wave of travel. Okay, the reflection of pulses from a fixed point. Okay, and so if we have our incident pulse moving towards a fixed point, the reflected pulse would be equal and opposite, kind of in their different directions. So reflection from the fixed end of a spring causes the pulse to be inverted. Okay, the speed of a wave depends only on the physical properties of the medium. The medium is kind of what's passing through: air, water, whatever it's in. Okay, the length, okay, L of the pulse, depends on the speed of the pulse and the time taken to complete the pulse. The length of the pulse is the distance traveled by the pulse in the time it takes the source to create that pulse. Okay, waves in the medium. So again, like when we're thinking of waves, okay, the direction of motion, okay, at this point it's coming up and then down, and it reflects. And so the motion of the wave within the wave, okay, each one, it's almost going around like this. Okay, so transverse waves can only travel on the surface of a fluid. Okay, waves within a fluid must be longitudinal, known as pressure waves, consist of compressions and rarefactions. Okay, this examples out of your textbook, you can read over that. Okay, waves are a form of simple harmonic motion, which we talked about in chapter 7, okay, because they're trying to kind of go back to equilibrium position, okay, and they're equal and kind of opposite as they go. So the particles of the medium oscillate in simple harmonic motion in response to traveling in the waves. Okay, some different equations. So wavelength is lambda here, okay, is equal to your speed times the period. Okay, you can, and again, remember that t is equal to 1 over our frequency. So if we are given our frequency instead of our period, we could always put into the formula that our lambda equals v over f. Okay, or if we're rearranging that, v is equal to the frequency times our wavelength. Okay, and this form right here is known as our universal wave equation. Okay, constant frequency, speed, and wavelength. Okay, we have one of these at the school. We would have done some different wave generating examples and stuff, but since we're at home, we just get to think about it. I'll try and post some videos kind of showing what's happening. Okay, but we have constant frequency, speed, and wave. So a wave enters a new medium, it will change speed, and the wavelength will change proportionally. So here we have like deep water. Okay, we're going to have higher speed. Whoops. Sorry. Okay, so this is a ripple tank. So we have deep water on this side, and then it gets shallower. Okay, and so the shallow water slows the speed down, okay, which then is going to decrease our wavelength. Okay, again, read over these pages in your textbook. Okay, look over the practice problems and so on. They'll just help you as you're working through your workbook. Oops.